This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And that's all that happens. So when I match that coefficient to that, right, I get, let's match that coefficient to that. It already tells you straight away that little k is equal to 0.5. Right? I match that coefficient to that. It tells me this equation here. But I know what little k is, so that's really a relationship between little r and big K. And I match that coefficient to that gives me that equation. Because I know what little k is, this is really a relationship between k and r. So I've got these two equations that relate k, big K and little r. Two equations, two unknowns I can solve. Right? If I substitute that into there, I get a quadratic in r that has to be equal to 0. So there are two values of r that make that equal to 0. And once I've figured out what r is, I can know what big K is, and I already know what little k is. So those 2 points there are these 2 points. 5 plus or minus root 15. Right? Of course, the zeros of this are at minus r, right? So you get 1 at minus 15 plus root 15, and you get 1 at minus 5 minus root 15. But that's all that I've done there is just said, you've said, what's that point? And I've said, well, how do we characterise that point? That's how we characterise that point. That's what it means for a quadratic to have both of its roots in the same spot. It has to look like a perfect square. Right? And then, go on.
Yeah, sorry. Are you saying something?
That's all right.
Yeah, it's also like in the plot, like my asymptotes was pretty inconsistent when I calculated without using the formula. Because I got S3 and then, but according to the plot.
Well, let's work it out. Sum of the poles?
Yeah, that's minus 2, sum of minus 3.
Okay. What does it mean? What does it mean for an asymptote to be anchored somewhere when that asymptote is at an angle of pi? I can anchor an asymptote that goes to at an angle of minus pi here. I can anchor it here, I get the same asymptote. I can anchor it here, I get the same asymptote.
Okay, so
when it's relative degree 1, as in this case, the anchor is irrelevant because the asymptote is always at minus infinity.
oh, okay.
Right? Whereas when I've got relative degree 2, then I've got asymptotes that go to plus pi on 2 and minus pi on 2. Now the anchor matters because that's a different asymptote to this asymptote. It's different to this asymptote. What's changing between these asymptotes is the anchor point. Right? Whereas here, I change the anchor point, it doesn't change the asymptote.
Because it's always a minus pi.
Well, because it's always, but this is always pi on 2, that's always pi on 2, that's always pi on 2. But clearly, they are different lines in the complex plane. Whereas here, when I change the anchor point, I get the same lines. I get the same line. They sit on top of each other. Right? Same for relative degree, anything bigger than 1. Right? If I change the anchor point, I change where the lines are. So for relative degree 3, you get 3 asymptotes. Right? And it corresponds to what the root locus of that looks like, as we discussed in the lecture. Right? 1 will go that way, 1 will go that way, and 1 will go that way. That angle there will be pi on 3, that angle will be minus pi on 3. Right? Now, so your asymptotes are a line, and they're asymptotes. It's not that the root locus sits on those things, it approaches those things. That's what it means to be an asymptote, right? if I anchor the points like this, I get different asymptotes to anchoring the point like this. This asymptote stays the same, but these ones have moved. Right? This one is staying the same in the same way that this one stays the same. Right? But the other two are different depending on where the anchor point is.
So it all boils down to the position of your poles.
The relative degree.
Oh, sorry. Yeah, the relative degree as well.
Well, it matters for anything that is relative degree 2 or more. So there's only one case where it doesn't matter, and that's when it's relative degree 1. And it's clear where it doesn't matter. It doesn't matter where the anchor is. That sigma is the anchor of the asymptotes. So it may have nothing to do with the points on the root locus at all. It's just anchoring the asymptotes, and the root locus will approach the asymptotes for large K. Make sense? Right? So that's why I encourage you, think about what these things mean. Don't just try to remember stuff, because if you thought about what it means, sigma is an anchor point, then you will have looked at a number and said, well, it's 3, who cares? Doesn't matter. Doesn't matter where I anchor a line going to minus infinity along the real axis. It still goes to minus infinity along the real axis, no matter where I anchor it. Right? So if you try to focus on the meaning of things, rather than just formulas I need to remember and plug numbers into them, right? Monkeys can do that. There's nothing interesting to come from that, right? Think about the meaning, right? What does it mean for it to be an anchor point? Does it matter when the corresponding asymptote is just the real line? Make sense?
Yeah, true.
Okay?
Yep. Just one more, but I think any can go. So I can do it. You guys want to go ahead?
I had the same question earlier.
Okay. You've understood now? Yeah.
I have a quick question about a term you use. I think I'm not confused. Velocity feedback, is that just the physical meaning of putting a zero at the...
No, it's the physical meaning of this. It's the physical meaning of measuring the velocity and feeding it back. What am I doing in this block diagram? I'm measuring the angle and feeding that back, and I'm measuring the velocity and feeding it back. So it's velocity feedback.
Yeah. Okay. All right.
That's all it means, right? It's describing the feedback path,
Right.
or
Okay.
just a part of it. Yeah?
Yeah.
You go ahead.
No, I don't know what if we had 4 points only, 4 root locuses? Like we had for 3, right? For 3 roots. We said if you don't find the equation, you can identify it's going decaying and.
Oh, look, when you've got higher order polynomials, all of this stuff becomes hard.
Yeah.
Yeah.
So we then we have to use the equation. Like we can't figure it out. It's like going in a.
Or even with the equations, you may not be able to write down the equations, because how do you write down where the zeros of a quartic polynomial are? There is no closed form way of writing it down.
So we can only limit our regions up to 3 degrees of polynomials.
Well, yeah, depends on how much intuition you have, right? But I could only write down exactly what the equation was because it was quadratic,
Yeah.
right? If it's not quadratic and I can't write down explicitly where the zeros are, I can't write down that equation, right? And then you resort to computers, right? All the computer does is it goes and calculates it. It sweeps across K.
Yeah.
For each K, it gets a polynomial. It finds the roots of those polynomials, puts it on the plot. Right? The computer's not following the rules. The rules are tailored to, humans being able to do it. Right? It's not tailored to computers doing it. Computers just numerically figure out where the zeros are for each value of K in a grid of values. Right? But like I said, to answer your question, right, in the lecture, it's like, does it matter what it is exactly? Right? If we're trying to just get this qualitative information from the plot, doesn't matter.
Yeah.
Right? No matter, it didn't matter if it went like that, right? Or if it went like that. It didn't really matter. The qualitative information that we could draw, we could conclude, is the same, whether it's this or this.
But with the change in the angle, the K would go.
They would have to meet in the same spot, right?
Yeah.
Okay, but I'm saying, does it matter if it does that, or does it do that? We get the same qualitative information. Now, engineers work in both qualitative and quantitative information, right? When you're making design decisions, you don't want to necessarily have to compute everything to infinite precision. You just want to know, if I wiggle this, what direction is something going to move in? So you know whether it's worth pushing it in that direction or not.
But selecting a K at this point would make my system pretty unstable with this transfer function.
Okay, but that wasn't part of the qualitative information. The qualitative information was that we keep on getting faster.
Yeah.
Eventually, the oscillations go away. That's the qualitative information. That's the same whether we're here or here.
You can just say it increases and then it automatically increases.
Yeah, that was the qualitative information. Not the increases to this value and at this value of k and then decreases beyond that. No. That starts now becoming quantitative.
Yeah.
Right? Make sense?
Yeah.
Just one small note.
Mm-hmm.
So for regulative degree 3, is it necessary to know at what points the root locus crosses the imaginary axis?
Is it necessary? Depends what question you're asking. Do you care? I don't know. If you care, then yes, it's necessary. If you don't care, no, it's not necessary. Do you understand the point I'm trying to make? I mean, the question, you can't ask arbitrary questions like that. You either need to know or you don't need to know. What if I'm asking the question, does the system become unstable if I push the gain too high? Then I don't care, right? And all you need to know is that for relative degree 3, right, I will have asymptotes that are eventually in the right half plane, right? Whether it's anchored here, if it's anchored here, they still end up in the right. If they're anchored here, then you've got this guy, part of this asymptote is also in the right half plane, but you may not be anywhere near the asymptote. Out here, right, the root locus approaches the asymptote for large S, right? So even if it's anchored here, you've still got these two guys here that are in the right half plane. And that will always, bits will go here for large enough K. So it depends on the question you're asking. Do you care these are just the asymptotes crossing as well. Where the asymptotes cross is not where the root locus crosses. They're different things.
Maybe I was like, okay.
No, but I'm trying to make a very important point for you to realise here, right? That the question you ask is not well posed, right? And it's not well posed because you're not saying why you might care or not care about where the root locus crosses the imaginary axis, right? If you want to know the value of K that puts closed loop poles on the imaginary axis, then you can work that out. You have phi of S, right? What does it mean to have closed loop poles on the imaginary axis? It means there exists an omega such that phi j omega is equal to 0. Okay? Now, this will depend on K. Agree? All right. So, if you expand this out, when I evaluate at S equal to j omega, this thing is a complex number. In fact, it's a complex number for any value of S, except for real values of S, because we're dealing with polynomials that have real coefficients. Right? But generally, this function of S is a complex number. So it'll have a real part, right, which will be a function of K and omega, and it'll have an imaginary part, which will be a function of k and omega. And we're saying that that is equal to 0 plus j0. So what do I get? I get two equations.
Either k is equals to 0, omega is something, or omega is 0, you get k.
Two equations, two unknowns. I can figure out where omega is. I can figure out what k is. Now, these might be nasty nonlinear equations, so it may not be straightforward to figure out what value of k and omega is. But in principle, you've got two equations, two unknowns. Right? How did I get to this? By just writing down what it means to have poles on the imaginary axis. It means there must be an omega such that this is equal to 0. Right? That value of omega will be where the poles are. That's what we're looking for in solving these equations, in addition to the value of k that will take the root locus there. Makes sense? All that's required, there's nothing sophisticated going on here at all. What's required is for you to think about the problem that you're trying to deal with. In the end, there's nothing sophisticated, right? Nothing at all. Right? The key is to write down the thing you're interested in, just like trying to find out which point's on the real axis will be part of the root locus, and for what value of k. Yeah, that wrote down to saying, well, what form does this have to have? Well, to have 2 points on the real axis, it has to have the form times some other polynomial. Now, we were just lucky that we were dealing with a quadratic, but in general, this will not be a quadratic. Right? Could be cubic. In the case that it's cubic, I've got a degree 1 polynomial there. If it's degree 4, I've got a degree 2 polynomial in there. Right? And then it's going to be hard to match coefficients to find the things that we want to find, right?
Will there be any point where k is less than 0? Like
You're asking a different question.
Yes.
You can do root locus analysis for k ranging from 0 to minus infinity if you like, but then we write down the phase condition. We want this to be an odd multiple of pi, but we were writing down, you have to write down this. Sum of the right? We want that to be 2k plus 1 pi, right? Because we were saying k goes from 0 to infinity, we were saying that's always 0. But if you're now saying that k goes from 0 to minus infinity, then that becomes pi, minus pi, which we then have to take over to here, and then we're looking for an even multiple of pi instead of an odd multiple of pi. But the principle is exactly the same. That's why it's important to understand the principles, right? Because then you make small changes like this, and you can figure out what to do. You don't have to rely on, some rule, because you've understood the principle. Right? That's the only thing that changes.
is it the same thing if we are changing it to a positive feedback loop? Till now we are only discussing.
Yeah, because what happens if I've got a positive feedback loop? Right? So when I've got a negative feedback loop, right? The closed loop, if I look at, say, R to Y, then I'll get that Y on R, right? Well, what's it going to be? It's well, hang on. It'll be I'll just have to. So it'll be Y on R will be K F 1 plus K F S, right? If I have plus there, then what's going to happen is that's going to become 1 minus KFS. And I can do the same thing. Now, instead of studying 1 plus KFS, right, I want to study 1 minus KFS, but 1 minus KFS is 1 plus minus KFS. And so I just put minus 1. I just got to account for another minus pi radians of phase when looking to satisfy my phase condition. Nothing changes. From the perspective of the principle that you're applying. The detail changes because now I've got an extra pi radians of phase because I'm dealing with a minus sign there. But if you now look at positive feedback and you vary k from 0 to minus infinity, this becomes plus again. And then you're back to the standard condition. Make sense?
Thank you, Michael.
Thank you.
Thanks. Okay. Has anyone else got questions that they want to consider? No? Yep.
Sorry, it comes out to show you it, but it was that's the relative degree.
Yep.
And it's like the number of poles minus the number of zeros.
Correct.
N minus N.
Yep.
And in your working out, you wrote 0 minus 2 on 2 equals negative 1. And I was just going to do.
So that was the top bit, right?
Yeah.
That was for the anchor point for the,
anchor
asymptotes,
point,
right?
that's right, yeah.
So, the anchor point for the asymptotes. Yeah, this is only for the case that n is bigger than m, right?
Yeah.
Right? When it's the other way around, then the anchor point's at minus sigma. But sigma was the sum of the poles, sum of the poles minus the sum of the zeros divided by the relative degree. Right? So the poles were at 0, minus 2. Right?
Yeah, and 0. And we got
There are none,
yeah,
there are no
zero.
zeros, right? Divided by 2.
That's something. Yeah. Thank you. And that's for k when it's small, yeah? Is that right?
Right?
For all of k.
This has nothing to do with k. Well, in fact, this has to do with k large.
Yeah.
This has to do with the behaviour of f for large s. Right? Why are we interested in approximating the behaviour of f by this, right, when s is large? Because we know for k large we're going to go to zeros of f. And when n is bigger than m, f has zeros at infinity that behave like this.
Yeah. So it's just to create a model.
Yeah, this is an approximation, right, for how f behaves for large s. Right? Because the root locus of this is easier to study than the root locus of f. But this is only going to study the root locus of this, right, which has all its poles at, it has n minus n poles at minus sigma, or sigma, right? It's easy. If I've got 2, they go like that. If I've got 3, I've got 1 that goes like that and that. Now, of course, you know,
So this is explaining what I was talking about before.
yeah. But you're only approaching the zeros of f at large values of s for large values of k. And that's why these things aren't actually part of the root locus. They're asymptotes. The root locus approaches these for large k. Does that make sense? They're not actually the root locus.
Yeah.
Because this is an approximation that's only true
Well,
for large s.
yeah, that's what you're saying. You
and change the anchor point, right, that changes where the asymptotes are, right? And if it's relative degree 3 or more, there will always be some asymptotes that go into the right half plane, which tells you then that for large enough k, you'll end up with zeros of the characteristic polynomial in the right half plane, closed loop poles in the right half plane. Make sense? Thank you. Any other questions? You got a question? Yep.
With this example,
Yep.
if we want the transient to decay really fast,
You want to be as far this way as possible. Yep.
so since we have like two paths where it can go,
It's not two paths. It's not two paths. It's not two paths. For each value of k, you get 2 points,
2 points.
right?
Yeah.
And what this is showing you is how those 2 points move as we change k,
Yeah.
right? So for small k, we get a point here and a point here. We increase k, that one moves this way, that one moves this way. Then for a range of k values, we get points like this. And they meet together. So for a given value of k, I could end up with a point here and here. Right? So it's not as if there's two paths. This is the path. Like this. You see what I mean? Yeah, so it's not two paths. So as I'm increasing k, the 2 points are always moving away from the imaginary axis, getting faster and faster. Does that make sense?
Yeah. But say if we make k go to infinity, we would get 1 point close to -5.
Then one goes to -5 and the other one goes to -infinity. Yeah.
Then what's the transient decay now? Is it -5 or -infinity?
Well, the one closest to the imaginary axis dominates the response.
Oh,
So which one's closer?
the one close to -5.
Yeah.
So if you want to solve like the k value that gives you like the maximum like transient decay, the fastest one,
Yep, that's the value there.
how would we solve it?
Okay, let's have a look. So, let's just think about what we're doing, right? We're saying phi of s, right, was equal to, what was it equal to? S 0.5 s plus 1 plus alpha s plus 1 times k, right? That's what we're working with?
Yep.
All right. Now, we know that when alpha equals 0.2, that it looks like this. Right? We get these points coming in like that, then they split apart and come like that. Okay? And split apart.
Yep.
Right? So there is a value of k that puts the 2 zeros of this here, and there's another value of k that puts them here. Right, so let's just mark that. Okay, so for a value of k, right, then we've got 0.2 s plus 1. This function of s must look like s plus r squared times another constant, right? And that will be minus r. Right? So for that value of k, this polynomial has to look like a perfect square. That's what puts the two roots on the same spot. Make sense?
That makes sense.
So if you like, I should write down, well, there's going to be a red value of c, right, and a red value of r that puts them there, right? And similarly, there will be another red value of r and another value of k, such that this, whoops, drawing the things in the wrong colours, s 0.5 s plus 1 plus 0.2s plus 1, I'm going to get a blue value of k, right, and a blue value of c, and a blue value of r, right? That'll tell me this point. Agree?
Yep.
Right? So, how can I find the value of C, R, and K? Well, you can do this, right? I can write down what this polynomial looks like, right? So it's 0.5 s squared, right, plus 1 plus 0.2 k s plus k, right, equal to c s squared plus 2 rs plus, so that should be c r squared, right? So how can those two polynomials be equal? I've got to choose the parameters k, c, and r to make those two polynomials equal. Well, how can I make two polynomials equal? I just match their coefficients, right? So I get that equation, which tells me what c is.
Yep, it's going to be the same for
right? I'm going to get 1 plus 0.2k must be equal to 2cr. Agree? All right. And I'm going to have that k equals cr squared. Got three equations, three unknowns. I can solve for them, right? So this tells you what c is straight away. So this equation becomes 1 plus 0.2k times equals r.
Yep.
Right? And then I can use that in there to write 1 plus 0.2 times c, which is 0.5, right? So that'll be 0.1, right? R squared, right? Must be equal to r, right? And so there will be, that's if and only if r is equal to, well, minus 1 plus or minus the square root of 1 plus 0.4, right? I've probably made a mistake somewhere. Divided by 0.1. Anyway, I've made a mistake somewhere, I think.
Because it has to be just a pure, real number.
That is a real number.
Oh, yeah.
That's positive. But I've made a mistake somewhere, I think, because that's not the answer. Where have I made a mistake? Yeah, I don't know. But the point is you get a quadratic, right? So you can write down what the solution is for r, right? Once you've figured out what r is, then you know what k is. So I figured out what c is, what k is, and what r is. I'm getting two values of r. Well, there are two values of r.
Okay.
Make sense?
That makes sense.
Yeah?
The guys earlier, when they were asking about how you would solve for k when it crosses the imaginary axis,
Yep.
I didn't quite understand how you solve it.
Okay. If I've got a root locus plot, right, that does something somewhere, but it crosses, right, at j omega and minus j omega, right? There's always going to be it's always going to be a complex conjugate pair, right? Because we're dealing with, real rational functions, right? Or in the case of phi, it's a polynomial with real coefficients, right? So the zeros will always appear in complex conjugate pairs, or be real, right? So if part of the root locus crosses the imaginary axis, right, that means, so this thing in general, it's a function of s and k, right, really. And we're saying there's a value of k here that puts the zeros here,
Yep.
right? For S equal to j omega. That's what it means for the root locus to cross the imaginary axis, right? There must exist a k and an omega such that phi j omega k is equal to 0, right? In order for this to happen. So we're trying to find out what these are such that this holds. So we've got two unknowns,
Yep.
right? This is a complex number. It has a real part, right? And it has an imaginary part. And we're saying it must be equal to 0. What's 0? It's that. So I get two equations. Phi r j omega k equal to 0. Even though there's a j there, because I've taken the real part, this will be a real number, just like this will be a real number, right? Because I've split it up into the real and imaginary parts, right? So I get two equations that are real valued. Two equations, two unknowns. Make sense? So that's how you find the value of k and omega at which it crosses. Now, of course, these equations here could be really nonlinear, hard equations to solve simultaneously. But that tells you, that characterises the value of k and omega at which you get 2 points on the imaginary axis. Make sense?
Makes sense. Yeah. Thank you.
Okay. Any other questions, or we've had enough?
I have a question.
You have a question? Yeah.
Just want to mention, like, when we vary like k from 0 to negative infinity, right? You just have to account for the negative
Correct?
pi.
Yep.
I was wondering, but the way that the root locus moves is the same, right?
No, it'll change because now you're satisfying a different condition.
Oh, okay.
Well, it'll still start at the poles, right? So the reason, so we get the rule that it starts at the poles and ends at the zeros by looking at this. Right? That doesn't change depending on the sign of k. Right? When k is 0, it's like the roots of the numerator here are like the roots of d, which are the poles of f. That doesn't depend on the sign of k. So that rule stays the same. The rule that it ends up at the zeros stays the same because that's just doing this. Right? And when k is large, that becomes 0. The zeros of this are like the zeros of m, which are the zeros of f. To make that conclusion, I have not used the sign of k at all. Agree? So those rules stay the same. It starts at the poles of f and ends at the zeros of f. Right? Some of the zeros may be at infinity when the degree of d is bigger than the degree of m. None of that changes. That all stays the same. The analysis of the asymptotes stays the same. Right? Because that was just about approximating f. What changes is the phase condition, right? So the anchor point won't change, but the asymptotes, the angle of the asymptotes might change because now we're satisfying a different phase condition, right? So when we were trying to make the phase add up to an odd multiple of pi, right? And we had a situation like this. You want those little vectors, which each have an angle of pi on 3, to add up to an odd multiple of pi. And that would happen in that direction, and that direction. Where do they have to go in order to add up to an even multiple of pi now when we're considering negative k values? Right? So now we've got these 3 points here. We've got to find points such that the angles will add up to an even. Right? So how's it going to add up to an even multiple of pi? Well, if we go to a point here with 2 pi on 3, and I've got 3 of them, they're going to add up to 2 pi.
That's an even.
Right? That's even. I could draw... Right? That's minus 2 pi on 3. I've got 3 of them. I go minus. Right?
Minus 2 pi.
This one, they're all 0. That's an even number. So we've gone from a situation where the root locus of this for k bigger than 0 is something that looks like that. And for k less than 0, it looks like that. It's different. Right? So the angle of the asymptotes will change. The anchor point won't change, but the angle will change. Right? And for the same reason, the bits that coincide with the real axis will change. Everything's about satisfying the phase condition. So if you change the phase condition, that will change. And so you go from a situation like for k being negative, you want to be to the left of an even number. So what happens is that one goes that way, that one goes that way, and at infinity they wrap around.
Wrap around in the same sense.
Well, no, this one they don't wrap around.
Oh.
Here you just get one goes that way and one goes that way. Whereas, so that's for k less than 0, whereas k bigger than 0, they would have gone like this and split apart.
Oh, right. Okay.
Right? Why were the asymptotes like this when it was 2, relative degree 2? Well, because if I draw a little test point there for 2 poles, draw a little test point, I get pi on 2, pi on 2. That gives me an odd multiple of pi. But if I want an even multiple of pi, then I want to draw my little test vectors like that, or like that. And so they become your asymptotes. And that's what's happening there.
Oh, okay. I think I got it.
Right, so there's nothing to remember at all other than the fact that we're trying to satisfy the phase condition. We're trying to make k f x equal to minus the angle of -1. That's all we're trying to do.
So just the phase condition changes.
Well, because right, so the stuff we were working before says that that's equal to the sum of the zeros minus the sum of the poles. But now we've got this. When k is positive, that's just 0, so it doesn't count. But if k is negative, then that's equal to minus pi. We're still setting it equal to an odd multiple of pi, because that's what the phase of -1 is.
Oh, okay. Got it.
Make sense?
Thank you.
All right?
Thank you.
I have a question about the previous example. And in this example, like
It's relative degree 3.
yeah, but why this line do not intersect with the real axis at -1?
Okay.
Because
Let's just-
it
let's
is
just walk through.
like sum of the poles and zeros and
Divided by
this
the...
and minus im. Yeah, but after
Let's have a look. Let's have a look. So, what we're dealing with this. What is it? What are the numbers?
I plus 1 and
Yeah.
I plus 2.
Okay. So if I do the sum of the poles,
Yeah,
right?
and
There are no zeros.
mhm,
Well, okay. So there's this,
mhm,
right? There are no zeros. Then I divide by the relative degree.
yeah. 3. Yeah.
right?
It's supposed to be -1, but
Oh, okay. That's the anchor of the asymptotes. It's not where the points meet, which is what I said before.
yeah,
Right?
I know.
So
But
we've got
like,
here-
how to design the real point?
Well, let's do this. Let's do this.
Yeah.
This guy here is the anchor point
Yeah.
for the asymptotes, right? The asymptotes tells you what's happening when k goes to infinity, right? So this guy moves this way, this guy moves this way, and they meet and they approach the asymptotes. They approach the asymptotes. This is not this point here. It just happened, as I mentioned today, in this very special example that it coincides. But in general, it doesn't. Right? Because this is just the anchor point for the asymptotes, and the asymptotes are telling you how this behaves for s going to infinity. It doesn't tell you how it behaves everywhere. Make sense?
Yeah.
So it's telling you, yeah, it's at -1, but it's not telling you about where they meet. Make sense?
Yeah.
To figure out where they meet, we can say, well, our characteristic polynomial in this case is s plus 1, s plus 2 plus k, right? And where they meet, this polynomial needs to look like a constant times s plus r squared times, s plus p, where this guy, for the corresponding, so this will be a value of k, right? Puts them here. That value of k will also put something at minus p. Right?
Yeah.
Agree? So we've now got to find c, we've got to find r, we've got to find p, and we've got to find k, such that this looks like this. Right? So, how are you going to do that? We'll write down what this guy looks like. What does it look like? It looks like s cubed. It's going to be, what's the coefficient of s squared?
3.
Right, it's going to be 3. What's the coefficient of s? S will be 2s plus k. No, it'll be 2s, right? And then we'll have plus k. Is that right? Does that look right? S squared plus 3s plus 2 times s. So that gives me that bit there, plus k. What does this guy look like? This guy looks like c... Oh, let me just write it all out. S squared plus 2r plus r squared s plus p. So it'll be c. I'm going to get s cubed. I'm going to get p plus 2r s plus r squared p. Sorry, that's s, right? It's 2, so I've missed the s squared. The s squared. What's the coefficient of s squared? S squared is going to be p, right, from that guy, and then that guy, 2r, right? What's the coefficient of s going to be? The coefficient of s is going to be that guy and that guy, right? So it's going to be r squared plus 2rp, right? Plus r squared p. Right? So, c equals 1. Right? P plus 2r equals 3. R squared plus 2rp, right, which is probably better written to 2. And r squared p is equal to k. So, how many unknowns do we have? 1, 2, 3. All right, and we have 3 unknowns we can solve.
Do we need to decide the point every time when we draw the plot?
I don't know. It's like I said to the guy before. What question are you interested in answering? The question is too generic to have a unique answer. Right? Depends what you want to know. Do you want to know where that point is? I don't know. Sometimes, some situations you might want to know. Other situations you don't care. I can't answer the question, right? If you say, if I want to know that, how do I do it? Well, then I've just showed you how to do it. Do I always have to do this? The simple answer is no, because I can invent a situation where I don't care where that is, because I care where that is. Make sense?
Yeah.
I can't answer the question in the way it was posed, other than to say no. Right? But just by thinking about what you want. So if I am interested in that point, well, it's saying I want my characteristic polynomial to have a factor that looks like that. Because if it's got a factor that looks like that, then I'm going to get a 0 at minus r. Make sense? So by saying that's what I want, I'm writing down that equation on the basis of what I'm interested in. If I'm interested in these points, then I've got to write down something else.